back, everyone. Now it's time to dive into the intellectual core of today's event with the first plenary talk, and we are honored to have Sri Uday Raghunath Birje here to share his insight through a captivating talk titled Case Study in Fiber Industry. In this session, Sir will delve into the intricacies of the fiber industry, offering a detailed analysis through a real-world case study. Without further ado, please join me in welcoming Sri Uday Birje Raghunath to the stage.
Happy afternoon. So before I spend a few minutes on the topic, how many of you are from the first year engineering? Wow. You know, I think you're just 2 weeks old in the college, right? Huh? 2 weeks. When I started my engineering, in the first 2 weeks we were spending time getting ragged by the seniors. Whereas you are attending a fantastic conference. I mean, that is the kind of transformation that has happened in the education industry. So one thing I want to tell you, I have been associated with VIPS for more than 2 years now, and what drives me is the inspiration of chairman and vice chairman, and most importantly, Swami Vivekananda's teachings, because I stay close to an institution which was inspired by Swami Vivekananda. Do you know which one is that in India? Yep. Huh? What is it? Huh? DAV. No, I stay walkable 10 minutes from Indian Institute of Science in Bangalore. I think all that inspiration I get from, that was inspired by Swami Vivekananda. If you know it's more than 100 years old, you do some research, you will understand what was the kind of inspiration. I see the same kind of inspiration. Indian IISc of Delhi, he is here, VIPS. All the changes, all the initiative that we are taking is in some way inspired from Swami Vivekananda's, I would say, inspiration at IISc. Anyway, so I want to congratulate again Professor Nidhi Sharma ji. I forgot to mention, I think she and Vanita Bharadwaj ji, Bharti Seth, Dr. Bharti Seth, and the entire management for putting together, I'm repeating, putting together an initiative like this, exposing students to something very, very, I would say, innovative and futuristic, as well as in many ways what is required for the country today. Congratulations to you and the entire team, ma'am. So that is one. And second is, I must thank Nidhi Sharma ji and team, because I am getting an opportunity to talk about my core domain knowledge that I have in the last 30 years. I think it is for me, I'm proud to mention that here, you know, I have had the privilege of implementing some of the biggest networks in the country, which is what is driving today's internet, which means the foundation of internet was set up by me and my team about 25 years back, which is, I'm getting that opportunity to talk about that. Thank you for that. So let me ask, I think all of you are in first year, right? You just passed your 12th and, you know, you passed all the entrance exams and come into VIPS. As I'm repeating, you're extremely lucky to be studying in an institution like VIPS. I have a quiz for you. I don't know if I can give you an award, but what is the one single material, let me repeat, one single material that is driving today's internet? All of you know today our life is revolving, everything is revolving around internet, right? You want to call a cab, you use, you know, smartphone, internet, everything revolves around internet. Okay, what is the one single material that is driving today's internet? Today's internet. Any answer? Any answer on this? Huh? So what if I say I'll give you a small gift if you answer it right? Yes. Huh? Fantastic. Optical fibers. How many of you knew? I mean, I'm surprised. I think, and I'm really happy in one way because you'll possibly appreciate the, the importance of optical fiber. See, when I started playing around with fiber, I thought fiber means plastic. So actually it is glass or silica. Okay, so I'm going to share, I'm not a researcher or I'm not a scientist or even for that matter, I'm not a professor of the, of the caliber of people like Nidhi Sharma ji and Vanita Bharadwaj ma'am, who are experts in this topics. But I am an industry person who's had the opportunity to play around and implement, some real stuff in the industry using these materials. So it is more of a case study than any, in-depth technical presentation. This one. So we talked about Viksit Bharat. Let me tell you, I think every presentation across the country, when I go to IIM Bombay or IIT Jodhpur or anywhere in the country, I think it is my duty to remind all of you that India's 3 pillars from a tech point of view are these 3. India AI mission, India quantum mission, and India's semiconductor mission. And all these put together, there is more than 1 lakh crores of funding that is happening from the government, which means these 3 missions will not only drive internet, it will drive chip making, it will drive problem solving capability for the country, or so many other things that are going on in Viksit Bharat. So all these missions or all these pillars is what will require advanced material, okay? How many of you think still copper is relevant? Huh? Copper is, when I started as a young networking person, age of some 23 or 24, everything used to be copper. Electric wires at home, copper. You connect a music system, copper wires. You connect a, the laptop or a, PC to maybe the back-end data server. It used to be copper. There is a significant transformation that I have seen over a period of time. In fact, now it is coming to an extent that 90% of the networks are all fiber, which is glass, okay? So you will be amazed with the amount of fiber that is being used in the industry today, especially in the internet industry, okay? This video, please, can you play this video? So look at this video. This is the amount of fiber that is across the globe, undersea fiber. This one? Yes. Okay. I had seen some of the fiber that lands in India. Look at India. Quite a bit of fiber lands at near Bombay, where major service providers. Look at this. All these lines are fiber cables going across the world, connecting, and this is what carries internet today. You see that? Most of it is landing in Bombay and little bit in Chennai. So this is to the extent when I said internet is being driven by fiber optic, this is a fantastic picture. But this is at the, I would say, the broadband and the, I would say, the backbone level. But what is happening in the, at the front end level, you will also be amazed. So I had an opportunity of executing one of the biggest projects in the country. How many of you been on Konkan Railway? Anybody has gone on a Konkan Railway? I'm telling you, you take a train from Thane Belapur in Bombay up till Mangalore. There is no better tourism experience than that. It goes through something like 200 tunnels and bridges, rivers, mountains, and the most difficult terrain. And we executed a project when, one of my previous companies, 800 kilometer fiber network from Belapur to Mangalore. And when you have to go through this kind of a difficult terrain, the only material or only I would say kind of network possible was fiber optic, because it has to be long term. It has to last something like 100 years. It cannot be, when it is copper, difficult to maintain. So we executed a project which is 800 kilometers, and you see, I've just put some pictures of Konkan Railway. It goes through all kinds of difficult terrains and, bridges, rivers, tunnels or whatever. So, I don't have the time to get into the details of how we connected, but while the backbone was fiber from Belapur to Mangalore, the last mile connectivity, which means it came to, let's say, one of the stations in Udupi station to the ticketing counter was copper. Okay, so copper still existed to some extent at that time, but the backbone was all fiber. So we talked about, right, how many of you know FTTH? Do you know that? What is going on right near your home? There are people digging up trenches and laying fiber optic cable, which means the network that was copper, which was coming on like a TV cable, today is all fiber. Which means up till a sort of a set-top box, it's all fiber. And then from the set-top box to the TV, it's some kind of a copper cable. So which means the last mile continues to be copper, but the fiber, the backbone, all over the country, all major operators like BSNL, Airtel, Jio, Bharat Broadband, all the Vodafone, everybody is laying fiber optic cable. So I showed you an ad where little bit like you can say BSNL is one of the biggest, fiber optic, they have one of the biggest levels, but they are advertising at a village level, move to FTTH, fiber to the home. Unheard of, 20 years, why 20 years back? 10 years back, we were fiddling around with that, very, very, unmaintainable copper cables. And today, there are reasons why fiber is more important than other copper. And here, there is one more. India is building the biggest fiber optic network in the world, which is going to touch 230,000 gram panchayats. Okay, why am I saying this? This gives you an opportunity to innovate. One is maybe devices, applications around these high-speed networks. Can you connect 230,000 villages using copper? It's impossible. Difficult to maintain. Many challenges in copper. Okay, so just gave you some, you see Disney Hotstar. Today you have, IPTV. All that is possible only with fiber. Okay. This is the difference. A 2000 for strand copper can't even match maybe a 200 strand fiber network or 200 core fiber network. And it still has more capability. That's the difference. And still there is unlimited capability in fiber. Of course, there are challenges in fiber, but easily it can be mitigated. So here's the difference between copper and fiber. You see the kind of speeds copper can provide and fiber, 60 terabytes, and it can be extended further. The innovation that you can do is further with devices and with innovation, you can increase the speed, you can increase the capability of the fiber. That's the unlimited capability of fiber today. And you see the hindrance is the cost. $8 to $12 per feet, whereas copper. But I think, see, the one major difference is copper, there's a significant loss on copper. Means when you, transmit electrical signals, there's a significant loss on copper. But whereas fiber, there is no such loss because it's light, getting transmitted to the fiber cable. And just, especially for the new students, a typical what a fiber cable looks like, okay? So, I'm doing so much work with so many, industry partners on AI. I thought I will give you a view of how AI can play a role in innovation in material science. So this is a house where by just putting in a picture of AI, and transmitting it through a lens, you can, extract the materials used in that house, every material, including from the painting to the sofas or whatever material. So this is, the pictures are transmitted, or rather, fed into, on an AI platform, like a generative AI platform, and you get to see even the cheetah, picture of a cheetah, it has given the, what is the kind of, yes. So these are the innovations that youngsters like you, in the next 4 years, you're in first year today, in 4 years, you must ensure that you get involved in at least a few innovations of this type. There are thousands of innovations possible, but I thought this is the most interesting and easily understandable. I picked up this, okay? I have, by the way, when you're using AI, just ensure that you're actually using your brain and not, putting on a chat GPT platform saying that give me some innovation. It's not going to happen. Only you need to use your intelligence and brain to really come up with some meaningful innovations. And as I think all the speakers in the morning have mentioned, sustainable innovation. See, fiber technology is not new. It is more than 100 years old. But innovations have happened. The faster speed, lesser cost, and so many things over 100 years. But it's one of the most sustainable. All the deep sea cables laid, some of them were laid more than 100 years back. Okay, so one is when you're using AI, I make it a point to ensure that when you're using AI to innovate and create some newer materials, create some materials that will be involved in responsible innovation. Very important. I don't have time to explain what responsible innovation is all about, okay? So today you have great power on your hands. We are building one of a world-class center of excellence for AI and quantum technologies right at VIPS. There's so much of power that's going to be available very soon now. Use it for responsible innovation, okay? And that's it. I think you welcome to the India's new decade. I think out of the next 10 years, India's decade, I think you're going to spend most of you are going to spend 4 years. Wish you all the best and great innovative journey. And I think, you have the capability of disrupting the way today materials are being used, as well as wish you all the best to build make India a product nation in Viksit Bharat. Thank you. All the best.
Thank you, sir, for your insightful and thought-provoking talk. Moving forwards, we are privileged to have with us a leading expert in the field of quantum sciences, Dr. P.C. Deshmukh, who will be delivering a talk titled Complex Modeling of Advanced Materials that promise to be enlightening as it is engaging. I welcome you to the podium, sir.
Namaskar. Good afternoon, everybody. Coming after Udayji's talk is very exciting because you gave insight into today's technology in a very beautiful manner. Thank you. So, there is a pun on the word complex. Can somebody guess what it is? The hint was already given earlier this morning in the first session when I said that mathematics is important. And I said that I will be talking about it in my technical talk, which is now. This will change the slides? Okay. So, can somebody guess what the pun is? Complex modeling. What do you think complex is? Anybody? I've given a hint that it has something to do with mathematics. I'm going to talk about complex numbers, but we'll come to that. So this is, I'm presenting this talk on behalf of a collaboration we have between India and Canada. Ajay, Soni, the blue are from India, me and Ajay Soni. Ajay Soni is from IIT Mandi. And everybody in the red is from the University of Western Ontario in Canada. So this collaboration has been supported to a large extent by the Shastri Institute initially. So, okay, the middle one, here. So congratulations once again to all the organizers for a very important meeting on sustainable innovations, advanced materials. So in this meeting, you're going to hear about many things, and let's see, you will, I'm sure, hear about nanomaterials, nanotechnology, nanoscience, and these are the materials of today and tomorrow. Carbon nanotubes, graphene. You will also hear about biomaterials. Some of these will be replacing living organs in the human body. Some of ours are probably already have these. I often run into people with lovely black hair, but that's not real. We meet people who are as bald as me, but they have nice hairstyles. Many have false teeth, but there are many other organs which can be replaced by biomaterials. Aerogels are going to be very important. You know, they are amongst the most difficult systems to investigate are gases and liquids. Means certainly solids also, but gases and liquids, because they do not have an extended structure which is crystalline, which is a regular structure. That makes it very hard to understand gases and liquids. And aerogels combine these properties of gases as well as liquids. Then you have metal foams, which are coming up. So these are metals. They have flexibility, porosity, which gives them unique properties for applications in technology. Optical fibers, Udayji talked about it. There are young students over here. I would like to ask, can you name 2 Indians who have contributed enormously to optical fibers? One of them should have actually got a Nobel Prize for this work. Anybody? Dr. Narinder Singh. Now please Google and find out what is his contribution to optical fiber technology. He has made fundamental contributions which are so important that many people think that he should have actually got a Nobel Prize for this work. The other is Pancharatnam. Pancharatnam was a student at Indian Institute of Science. He studied under the supervision of C.V. Raman. And there is an important phenomenon which is known as the Pancharatnam berry phase. The Westerners normally call it only as the berry phase after Michael Berry. But it is based on the same idea which Pancharatnam developed in the context of optical fibers. And it is going to be of even more importance in the coming years because a technology to build quantum computers, the qubits are very unstable, they are very fragile, and to develop more robust quantum computers, you may need to use the idea of the Pancharatnam berry phase in an innovative manner. Then you have materials which are called as shrills. These are made from shrimp shells and biomaterials. They will have applications in surgical applications, medical technology. Then the two-dimensional materials, semiconductors, insulators, superconductors. So there will be very fascinating developments in this area. And then metamaterials. Metamaterials have very unique electromagnetic properties, electromagnetic and optical properties, where you have very strange behavior. You can have negative refractive index, for example. So these are some of the materials, and I'm sure that there will be some talks covering some of these areas and perhaps some more. There are lightweight materials which are very light, and their strength comes from hydrogen bonding. And these are polymers, polymides, and long chains of hydrogen bonded materials. Then technology is growing in the area of, where everything that you look around, there are colors. I mean, there are these red colored chairs. Everything around you has got colors, and colors are very toxic. How do you produce these colors? So this is where you need an ethical technology, which is what is meant by ethical colors. So this is coming from bacterial dyeing. And the bacterial dyeing, this technology is coming up in a very big way. It is scalable to the extent that it can meet the requirements of the society. It is 80%, it uses 80% less chemicals, which is really what makes it sustainable. It uses 77% less water, and it causes fewer than 31% of carbon dioxide emissions. So these are the things which are moving in the direction of sustainable technology. This is grown in bioreactors of this kind. And then you need different kinds of materials. In particular, I'm going to talk about the kind of material that is required for defense. And we have DRDO, Dr. Sushilji with us. So some of this work may be carried out in your labs as well. We have lost 2,000 soldiers at Siachen, and due to bad weather and such things. It's a huge loss. A single soldier life is something which causes, in the amount of pain it causes to every proud Indian is huge. And we have lost 2,000 of them just because of weather and climatic conditions. How do you clothe your soldiers? Now, the clothing should protect them from weather and also from bullets. So you need multifunctional clothing, and you need special materials for that. And I'm sure DRDO is engaged in extensive research on this, materials which combine the properties of metals, polymers, ceramics, composites of various things. So these are huge requirements of the future of generating multifunctional materials. Then you need energy. And you turn to batteries, but materials for batteries are scarce. Materials for fuel cells are not. So fuel cells, research in fuel cells is a very important domain of engagement. And then you need materials for quantum computing. Now, perhaps many of you are very excited about quantum computing, which is around the corner. It is already with us. Right now, there are very few quantum computers, but in another 5 to 10 years, there will be many. and you will continue to use classical computing, but in a different way. But the main challenge in quantum computing is that the qubits are very fragile. There is this problem of decoherence, and you can lose the entanglement very easily. So you need new materials for the hardware platform for quantum information processing. And if you just demonstrate the concept in the laboratory, that is not enough, because you need scalability, which is a huge challenge, and that is extremely hard in the field of quantum computers. So proof of concept research can in fact be misleading in this area. That is due to decoherence, as I mentioned. So fossil fuels, we will probably run out of these in 40 to 50 years. We will run out of natural gas. It's maybe certainly not going to last us more than 100 years. So how are you going to meet the energy requirements of the world? And then these fuels, fossil fuels, natural gas, they cause enormous pollution. Means these pictures are not, they are seen every day when you commute in Delhi or anywhere else in any city. So you need to mitigate this situation. You need new materials which will provide energy. And it is not easy, because we have from the earth enough for every man's need, but not for every man's greed. But these needs are growing all the time. You need novel materials for more energy, more electricity consumption, which is what this conference is about. And would it not be nice if you can convert heat into electricity directly? Because heat is generated, it is sometimes called as the most degraded form of energy. Because whatever you do results in some heat, some energy dissipation, and if you can convert it into electricity, that would be great. And it is this work that I'm going to be talking about, which is the focus of today's talk. And it will be driven by these two kinds of materials. One is the solar cells, and the other are thermoelectric materials. So here, solar cells and thermoelectric materials is the main area of our research collaboration, which I mentioned earlier, between India and Canada. The thermoelectric materials, you can have them on your wrist. You can have them in flexible form. You can have an energy management IoT tied up to that. You can have Bluetooth devices. And with this, you can have real-time health monitoring and so on. So these materials are of great importance, and what they rely on is conversion of heat into electricity directly. Now, you need high-performance thermoelectric materials. Basically what you're doing is all the waste energy, means you're burning some energy, some heat is being generated in your body, and you're trying to convert it into electricity. So instead of letting it go waste, you harvest it and convert it into electricity. And you need a material which can do that, and that's what I'm going to be talking about. Now, all this is very difficult to do, and look at the last line here, that the challenge comes mainly from the fact that there is lack of a good research roadmap. And this is where research is really challenged. And what you want to do is, you can't take up different materials and keep experimenting, find out does it work or does it not work. Okay, if you want a drug for cancer, for example, you try different drugs and you don't know what kind of a molecular structure the drug should have. So the alternative is to simulate this. So simulation has become a powerful tool, and you need to simulate materials with desired properties. And this is where modeling, mathematical modeling of drugs, or in this case, mathematical modeling of functional materials, advanced materials for sustainable innovation, you need to come up with very robust mathematical models. And I'm going to be talking about complex modeling, in which the word complex refers not just to the complexity, but to the use of complex numbers. And complex numbers, everybody, now that I have told you what the pun is about, complex number is a pair of real numbers. So if x and y are real numbers, x plus iy is a complex number. I is imaginary, it is square root of -1. But there is nothing imaginary about the imaginary number. The imaginary part of the complex number is as real as the real part, because it is a pair of two real numbers. It gives you the capability of handling two real numbers in one go in an algebraic scheme. That is not enough in quantum theory. That is not enough to describe nature. Nature requires the quantum theory. And quantum theory requires the complex numbers. It cannot be built by two systems of real numbers. You need a complex number at a very intrinsic level to build the quantum theory, but that's a much larger subject. I want to focus today's talk on solar materials and the thermoelectric materials. I'm going to talk about a mapping which is from a complex number Z to another complex number W, and this is a mapping. The WZ e to the power WZ, WE to the power W is Z. This is a mapping, and this has got a countable infinite number of solutions. This mapping, the function W is called as a Lambert W function. And this function has got very exciting properties, which provides the basis for our work, which is on the basis of the Lambert W function. There are a number of branches in the complex plane. The branches with k equal to 0 and k equal to 1, these are real values for any z. You have a principal branch for k equal to 0. This has got positive values in its range. The branch with -1 has got this range in its closure. This is a plot of W0 and W -1. And what this function does is something that I'm going to tell you. I will not get into the mathematics in too many details because it will not be suitable for this audience, but I wanted to let you know what this work is about. So here is some work which has been done by my Canadian collaborators, Kenneth Roberts and Sriram Valluri. They've studied this Lambert W functions. Those of you who have studied quantum dots, there are people over here who are studying quantum dots, nanosciences, nanotechnology, quantum wells, quantum dots, and quantum wires. May be familiar of the problem of a particle in a box, in a spherical box. And The quantum solutions for this do not have analytical solutions. You have to get the solutions either using numerical methods or graphical methods, but one can use methods of complex analysis, and this has been proposed by Ken Roberts and Sriram Valluri in a paper which is not very old. It came up in 2017, and they showed how to get the solutions using the Lambert W function. Now, what the thermoelectric effect is, how it gets used in designing the thermoelectric effect, because you need efficient thermoelectric materials for sustainable innovations. So, everybody knows the Maxwell's equations, I would hope, or at least is familiar with the Maxwell's equations. And this is the J equal to sigma E complements the Maxwell's equations. Maxwell's equations tells you about the fields, but then when you come to currents and fields and how the fields determine the currents, the J equal to sigma E gives you that relationship. And that is coming from a voltage difference, that when you apply a voltage difference across a wire, then a current flows. And the current flow is proportional to the voltage difference delta V. But you can get a current even by having a change in temperature. If you get two metals and you have a temperature difference between them, then you can generate a current which is proportional to the temperature difference. And that is what gives you the Seebeck effect, and the thermoelectric materials can generate electricity using this Seebeck effect. You can also have the converse effect, which is called as the Peltier effect, that when you pass an electric current through a junction, and then depending on the direction of the junction and some other intrinsic properties of the two materials, heat is either absorbed or released. And you can use this as refrigeration devices, if you like, or generate power using the Seebeck effect. Now, how do you improvise the efficiency of these materials? Because that is the main thing that you really want to do. And that is determined by what is called as the figure of merit, which is a measure of the efficiency of a thermoelectric material. So, as you see, the efficiency of a thermoelectric material, which is indicated here by a figure of merit, is driven by the two constants sigma and kappa. One is sigma is the electrical conductivity and kappa is the thermal conductivity. So their ratio is involved in determining the efficiency of these materials. And this ratio is a constant according to a law which is quite old. It was formulated in 1853 by Wiedemann and Franz. It's known as the Wiedemann-Franz law, that this ratio is a constant proportional to the temperature. The proportionality is the Lorentz number. What essentially this law tells you is that good materials which are good conductors of electricity are also good conductors of heat and vice versa, which is our common experience. But this law is not exact. It fails, and you really need to find out how to improvise the figure of merit of a thermoelectric material. This is where the mathematical modeling comes into the picture, because the constant sigma and kappa can be calculated using rigorous mathematical methods. So this is where the Lambert W function comes into the play. This is my student Akash working with Professor Valluri in my apartment after dinner. And Akash has done brilliant work in this. I'm very proud of it. So constants of proportionality, kappa and sigma, these are determined in terms of certain integrals. And these integrals are called as Fermi-Dirac integrals because they appear in Fermi-Dirac statistics. There are corresponding integrals which are also known as the Bose-Einstein integrals, which come in the Bose-Einstein statistics. So these integrals have to be calculated, and sigma and kappa are given in terms of the Fermi-Dirac integrals. And this is Akash's paper, which is about 5 years ago, but in the last 5 years we have done considerable work since Akash's first contribution to this field. Essentially what we do is to calculate the exact Fermi-Dirac integrals and arrive at a generalization of the Wiedemann-Franz law, which I told you is not exact. It is a good approximation. It provides a limiting behavior, and you can get information about these mathematical functions from either the National Institute of Standard Technology, the tables, the NIST handbook tables, or tables by Abramovich and Stegen, for example. It is aimed at obtaining corrections to the Wiedemann-Franz law. And these corrections, you need to study the behavior of electron dynamics in metals, and that requires information, understanding about the scattering parameter. And in terms of the reduced chemical potential and the scattering parameter, you can determine these, you can carry out these calculations. You get tremendous insight into the mathematical expressions and determine a mechanism to optimize the figure of merit of thermoelectric materials. The thermal conductivity comes not only from the motion of the electrons, but also from the lattice component, the lattice vibrations, the phonon contribution. And the phonon contribution can also be evaluated much more accurately using this. The mathematical expressions are complicated. They involve the Fermi integrals, polylogarithm functions, and I will not get into these details. But that is something which, what I would like to underscore is the fact that Akash, whose picture I showed, started working on this project with me when I was a student at IIT Tirupati in the first year. So he was a first year student just like any one of you. And by the time he graduated, he had published this paper. Do you see your opportunity here? The first year students who are over here, I want you to recognize your opportunity over here. You can get involved in these studies. I will work directly with you. I will put you in touch with Professor Sriram Valluri. And you can contribute to frontier research even as an undergraduate student at the Vivekananda Institute of Professional Studies. So Akash calculated some of these Fermi-Dirac integrals and obtained these optimizing functions. You can see that there are various maxima and so on over here. So you actually get a scaling of the Wiedemann-Franz law. The K over E is a constant, K is the Boltzmann constant, but there is a correction factor which is the function A, which rectifies for the Lorentz constant, which is not a strict constant. And you need to do this by studying these maxima and minima in these functions. You can come up with mechanisms to optimize thermoelectric materials, their efficiencies. The other application of the complex numbers of the Lambert W function that I'm going to talk about is the applications in solar cells. Now, I'm sure everybody knows that this is an alternative source of energy that everybody is hoping to tap into. Now, consider this solar panel on the top of a car, and it converts solar energy into electricity which gets utilized in the car. It adds 5 kilometers per day of mileage to the car. Just imagine how many cars are running in every city, in every country, and the amount of advantage you will have. Now comes the difficult part. What happens to these solar panels when the car is going on a road like this? Every solar cell on that panel on top of the car is not receiving equal light all the time. Okay, because it will go under a shade of a tree, it will come out of the shade, and this is happening dynamically. Now, what happens to the solar cells? Now, they are acting in series, and if one solar cell is generating electricity which is not able to pass because there is a shade, a transient shade, okay, it's going to create heat, and the solar panel can get damaged. Now, this is a big problem. So you need to model this, and modeling this involves mathematics. This is done using complex functions, using the Lambert W functions, the polylogarithm functions, and these have been studied in our research group. So to mitigate situations of this kind, you need to do a lot of simulation work, very advanced mathematics. This is again done by students at IIT Tirupati. Sibi Balan and Prabhat again started when they were first year students. So Akash is not the only one. There are plenty of opportunities. I've done a lot of work with undergraduate students. And I hope that we will have that culture right here in this hall. Not just Prabhat and Sibi Balan, the third author, the first author is Prabhat, second is Sibi Balan, the third is Aditya Chaudhary. I did not have Aditya's picture over here to show, but he was also their classmate. So Prabhat, Sibi Balan and Aditya have played the lead role in this. They have determined the efficiency of solar cells using the Lambert W and the log-right functions. When you use the log-right functions, you get certain numerical problems, you run into some numerical overflows and so on, and how you go around it is by using the log-right function, which is the work which was done by these three students. Very nice work. So they generated algorithms, did calculations. These have been published in a conference in South Africa last year, and then it came out in an IEEE journal. It's very exciting when you see undergraduate students publishing work of this quality. So, as I mentioned, they help improve the numerical accuracies in this. These are some of the other students. On the left, is Akash. Then next to him is Pranav Manangat. Next to him is Harsh. Harsh was a student at IISER Tirupati. He also started working with me when he was in the very first year, just out of high school. Just out of high school, and by the time he comes to the fourth year, in those 2, 3, 4 years, they learn all the mathematics, the physics, the applications, the numerical methods, the computing, building the algorithms. And by the time they get to the fourth year, they publish something like this. This is amazing. I'm very proud of this one. Next to Harsh is Professor Sriram Valluri, who is the main expert in this field. He is one of the world's leading authorities on the LabW function. I'm very privileged to have his support and have his guidance. So I've been working with Sriram Valluri for more than a decade now. Our collaboration started in 2011. And this is Aditya. He's one of the authors of the previous paper who I mentioned. So what they have done, this paper, this is, they have developed mathematical models to simulate the behavior of solar cells using the logarithm function, which is a transformation of the Lambert W, and it improves accuracy and speed of these calculations. So I think this is my last slide. The first picture is that of a quantum well. It's a particle in a box kind of thing in one dimension, which some of you may be familiar with. This is the problem for which Ken Roberts and Sriram Valluri provided solutions using the Lambert W functions. Otherwise, they are amenable only to numerical or graphical methods. The second figure is roughly the opposite of the previous one. It has a potential barrier, and one of the mind-boggling phenomena in quantum theory, it is actually a mind-boggling phenomenon in nature, that even through a barrier, a particle can tunnel through. That's called tunneling through a potential barrier. And this has got certain similarity with optical properties, which is called as frustrated total internal reflection. Right now I'm working on the frustrated total internal reflection with which is with another student from IISER Tirupati. He did this work a few years ago. A student by name Zadhav. So he has done some very good work. We are writing that paper now. This has got important applications in modeling quantum dots, microelectronics, and even metamaterials. So these are very fascinating applications of these methods based on the Lambert W function. And I told you that I will comment on the importance of mathematics, which is going to be a quotation from Eugene Wigner, and I am going to end my talk with this quotation. So Eugene Wigner, he wrote a paper in 1960. The title of the paper is The Unreasonable Effectiveness of Mathematics and Natural Sciences. It's almost unreasonable. It's shocking, but it works. And what he wrote in this paper is that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. It is a wonderful gift. It is a very powerful gift, and it is up to us to use it. It's a very powerful gift. I talked about complex numbers, complex analysis. I talked about quantum theory. The quantum theory is basically a mathematical framework to describe the laws of nature. It's based on linear algebra. But it works. Do we really understand it? We don't. In fact, Feynman went on to say that nobody understands quantum theory. Niels Bohr said that if you're not shocked by quantum theory, then you have not understood it. We don't understand all the intricacies, but we can use it. Thank you very much. If there is any question or comment, I will be happy to make an attempt to respond. Yes, please.
Thank you, sir. It's a very eye-opening talk. Learn a lot of things here. So I have two questions, sir.
Yes.
You talked about the polyamide material, which is stronger than steel. So this polyamide material is also used for membrane, the reverse osmosis distillation system.
Yes.
So the problem there is to have a membrane which will require lesser pressure to sustain. So is that something done on that aspect?
I do not know, but I presume that it can be studied. I'm not personally aware of a specific application in the area that you are talking about, but that's something that I can talk to my colleagues and find out if they know anything about it. You have one more question.
One more question is, I just also learned about this new material for thermoelectric generator.
Yes.
So this is figure ZT, figure of merit.
Yes.
So whatever work I understood is this was basically the already developed Lorentz number is there.
Yes.
So and your work is basically a new equation for that Lorentz number.
It provides a correction to the Wiedemann-Franz law.
Okay.
So with the Wiedemann-Franz law involves the ratio of the thermal conductivity and the electrical conductivity.
Okay.
And the proportionality involves the Lorentz number. So the
Lorentz number is a universal constant. But then there is a correction to it, which can be obtained using the methods, the mathematical modeling that we have done. Because what we do is the mic on?
Yeah. So the mathematical modeling that we have done, it calculates the conductivity, the thermal conductivity and the electrical conductivity using rigorous mathematical functions, which are the Fermi-Dirac integrals and the polylogarithm functions. So using this, you can calculate the ratio much more exactly. So the Wiedemann-Franz law gets modified, gets corrected, and then you can determine the efficiency of the thermoelectric material appropriately.
Okay.
That's
Sir, is there any new material or new development on the materials to improve ZT?
okay. So that's a very good question, and that's exactly where our collaborator Ajay Soni comes into the picture. Ajay Soni is an experimentalist. He is at IIT Mandi. He's on the faculty there, a good friend of mine. And using our formulation, Ajay is now trying to build new materials which can reproduce some of the advantages which come out of these calculations. So we have not succeeded at that as yet, but Ajay is putting in a good amount of effort in this. And this is where we really need collaborations, because it is impossible for a single person to have capabilities in experimental science as well as theoretical science, computational skills and so on. So we are very fortunate to have this collaboration in which we have experimentalists from IIT Mandi and a theoretical group from the University of Western Ontario. So I hope that we will have something to report coming from Ajay's lab. Thank you. Any other question or comment? But I'm very easily reachable, so feel free to send an email to me and so on. So Vinit ji has my contact. So thank you very much.
Thank you, sir, for that truly inspiring talk. I now request our Honorable Chairman, sir, and Vice Chairman, sir, to please come onto the stage and present a token of appreciation to Professor Deshmukh. I now request Professor Shri Uday Birjeji to come onto stage for the token of appreciation. I now request all our guest speakers to also come to the stage for a group photograph with Vice Chairman and Chairman, sir.
We are not discussing for that.
I'm jumping in for just a minute to tell you that Dr. Sushilji has just told me that at the solid state physics laboratory here in Delhi,
this what I'm going to talk actually,
Yes.
this material itself shows all these properties.
Yes.
I'll
introduce
so I will
Yes.
tell you how that is working. So you can find the
Yeah.
new materials they can
So we just decided to enter a collaboration.
Because of the time constraints, we're continuing with the keynote talk and we'll break for lunch a little later. Our first keynote speaker is Dr. Sushil Kumar Singh from DRDO. Since joining SSPL in 2008, Dr. Singh has led several R&D projects, including silicon carbon bulk single crystal growth, MEMS-based adaptive mirrors, and multifunctional thin films for defense application. Dr. Singh has been instrumental in bridging the gap between nature and technology, and today he will be sharing his insights in a talk titled From Nature to Sustainable Technology, Transforming Silk Cocoons into High-Tech Solutions. Please join me in welcoming Dr. Singh. We're eager to hear from you, sir.
Thank you. First, I would like to show my gratitude to the organization of VIPS who have given me the chance to, I'm here talking with you. Here actually I'm working with the solid state physics laboratory DRDO, and we are working with the various technologies, semiconductor based technology. We are making MMICs. We are giving the full solution basically to the from the growth of the material to the fabrication of the device. So we have all the facilities for that one. We also have our foundries. We have the foundries GATEC, also for where we make the MMICs and give this product to the nation. Also for the ISRO, our 20-30% of the ISRO product we generally give through the GATECs. We also have the MEMS-based foundries in the Bangalore. Okay, is the StarC, and there we are making the various MEMS-based device. So here in SSPL also, we have developed the full solution, means from the wafer to the device. Okay, we developed the facilities called the silicon carbide-based wafer, 4-inch wafer we are growing in our laboratory. Okay, and also making the various devices using that one for the gallium nitride-based MMICs, which is useful for the high frequency, high temperature applications. So, and it's myself, I'm also presently I work for the silicon carbide, developing that facilities. Now I'm working for the projects called the early warning system for the landslide application. So in these applications, basically we develop the acoustic emission sensors. So when you see maybe you tear any paper, if I tear any paper, the bond will be break, with the acoustic waves will be generated, that sound. Our sensor is very sensitive to detect that small signals. Okay, and this is indigenous. We are developing this technology in India, and compared to the sensor which is available in the market in the physical acoustic USA, the cost is 10%. There we are making in the maybe 2 lakhs per sensor. Here we are making in 10,000. Okay. We already given the TOT to the one company in Kalyan in Mumbai, and we're making the acoustic sensor with the various frequencies. So basically, when you can see the now lot of the problems about through the weather, climate changing, landslides, snow avalanche, so many problems in the worldwide we are facing now. And can we issue some warning for that one? Basically, we measure the health of the hills. Okay, and a small deformation in the hill we can detect and issue the warning before time. Okay, we can know the just like a health of my body. I can know my body health, how many percentage. We can issue the health of the hills. We can give the how much percentage health of these hills are there. Okay, when we reach to the 80-90%, we start giving the warning. So we already have did the R&D in the SSPL. Now we are putting on the field. So I putting my system in the Narendra for the landslide. Also Manali Leh access is very crucial for the defense application. So we are putting for the snow avalanche. We have put the server system in the Banyal top, north and south. There also we are testing our system for the snow avalanche. Also in the Manali Leh access, we have put our system. So we are giving the total solution nowadays. Our working is changed now to the DRDO. Earlier we were making the component, giving the component particular, but now we are giving the full solution. So for this one, I'm a project director for that one. I'm giving that. But here I'm very happy actually. Dr. Desmukh is giving the topic where he has chosen the lot of the material, sustainable innovations. Okay. So this way he have given the porosity, thermal, electric, and also the nano and various form he have shown, and on the fibers also. So this, how we are get the idea. Okay, this is from the nature. How we are getting the idea from the nature, how we can understanding that one. So it's very important for the student especially. Okay, this talk I designed for the students. See, when they start doing the, I'm scientist. Okay, I don't know the authority. I don't know the this one. I'm experimentalist. Okay, I do the experiment. I understand, or I will give the okay. I understand that one. This is working for me. So this way, how we start thinking for the experiment. Okay, I will try to give that cue to the students. So can students who is new in the research, they can start thinking for the research opportunity and how they can think, how do they work. So here I'm talking for the nature of the sustainable technology, transforming silk cocoon into the high-tech application. So, see, we know the sericulture. Sericulture is very, in China and India, the sericulture we are doing. Sericulture means what we are doing, the sericulture, the process of the cultivation of the silkworm, rearing of the silk, and to the silk production. Okay, this is, here we have the in sericulture we have the arts as a science. Both are involved there. And this one, in this one, we have the two types of protein. One is called the fibrin. Fibrin is 80% and sericin is 20%. And sericulture have the three processes generally. One is a moriculture, where the cultivation of the leaf. So actually the leaf quality, what leaf is cantilever is eating, they grow the property of the silk. Okay, we can fill the various nanoparticles to the leaves, through the leaves, and we can improve the property. We can change the color of the sarees or the silk, color of the silk. So these are people is working in that direction. They are working, they have the silk raying, silk, this one. In India, we have generally 5 types of silk there. This is the mulberry near to the Bangalore in that area, Ramnagar and this thing. We have the Tasar silk in the Chhattisgarh area. We have the ox in Kashmir here. And then we have Iri in the Punjab or West Bengal. And this the More silk that is in. So this way I'm just giving the idea. I'm not talking about this one, I'm working in this one. I'm giving how the sericulture is working and people. And this cycle is very important actually. If we can understand this cycle, how that is working, then we can know this. Earlier we have the actual silk moth. Silk moth lay the eggs. That eggs basically will develop as a larva, and that larva he continues the leaves. This is the feeding time. We can feed the leaves to the larva, and after the feeding the leaves in 10-15 days, then he start making the silk fiber. Okay, he make the silk fiber surrounding him. Okay, and he protecting himself. Okay, he go in this cocoon and for the dormant phase where he's going to grow. So he's protecting ourselves from the environment, from the different factors, and then after the growth, he will come out from that one. So this is he will work like this, and this is in Chhattisgarh generally, they do the moth coupling, how they do the moth coupling, laying the eggs, this one. So this is the basic technology. So this is basically going on. Now we start the thinking of the scientist. Okay. Now, see, this is also where just like gel and they make for the silk now. So many, these are fibers, gels, sponges, okay, also microspheres, films, tubes, and also the lot of the unique application they are having in this one. Okay, for the biomedical industries. Okay, but now start from the when I actually joined India back. Okay, I have this question from the long time. Then I say, okay, main question was there, how the pupa survive and grow under the protective environment. We go in the closer, but how is surviving there? Okay, so this we don't know how the brain cell of the dormant pupa sense the environmental factors, just like this enclosure inside this temperature, humidity, okay, and how they sense that one. So these are the second questions basically. So basically the silk we grow in the tropical and subtropical region. Okay, where we have the more heat and humidity, atmosphere. Okay, the weather is very different there. So maybe the factor is possible that the intrinsic factor, the temporal electrical firing of the neurons, secrete brain cell to the dormant pupa, or environmental factors like temperature, humidity, light. So this factor is possible. So what we start from the beginning. Okay, we know the zero, we don't know anything about that one. What we'll do, we just cut our silk cocoon, okay, in the two pieces and see how it's looking in the microscope. We see the one surface, inner surface is very fine and outer surface is rough. We more closely we can see. When we see the more closely, we can see the crystals. We can see that some crystals are there in the outer surface, not on the inner surface. So we say, okay, we see how this, what is these crystals. Then we identify these crystals as a calcium oxalate monohydrate. Okay, so this, we do the various experiments. We have to find if it's real or not. So we can have the pure calcium oxalate monohydrate, and then we etch from the silk cocoon itself. Okay, we remove this one and see, and we study. Okay, and then we make a confirmation that okay, this after removing this, the surface is smooth. We do the IR spectra. Okay, so basically what we are doing, we are making confirmation. Okay, is okay, what is there with the various characterization techniques, we can do that one. Then we see what present is inside the outer inner surface, which type the elements are there. So we observe, okay, in the outer surface we are having the more oxygen, calcium, also carbon is there, okay, some cobalt and manganese may be there, but in the inner surface we have the more carbon, also the some nitrogen is there, also the magnetic materials, manganese, Fe, CO, cobalt, so we see, okay, we have this side element there. Then we make the simple laboratory experiment. Okay, see how the CO2 will be diffused in the cocoon. Okay, so we'll see so what we have discovered basically, the small CO2 can come out easily, but not diffusing inside. So it's the getting. Okay, so the one-way traffic is there, coming out, but not going inside. But this case is not in the oxygen case. In the oxygen case, this the rate of the also the same, more or less. You can see the rate of the cocoon going inside the gas, but we can oxygen both the flow. We are having inner going the out. Okay, due to the arrangement of this calcium oxalate crystal, maybe we may be. So then the temperature. Okay, when we see the temperature, the outside temperature is 5 degrees, the inside temperature is maintaining around 25 degrees. When the outside temperature is 50 degrees, we are observing 32 or 33 degrees centigrade inside the temperature. So we find that the result demonstrates that the CO2 getting and the thermoregulator help in the maintaining the ambient pressure inside the cocoon for the growth of the pupa. So itself is temperature, pressure, and these are maintained inside. And also this is can work as for the gas filter, for the energy saving home. So various applications is possible for that one. So this is from our first beginning into 2012, we have published the first paper of this one. After this one, we see the questions comes. If electricity is there or not, because we have the static electricity, the silk cocoon, when you are wearing the sari, some water portion which go there, you can have some current there. So if any type the electricity is there, we can get the electricity from the silk cocoon. So you know this is the earlier report by the Hornes Matthew given by the one Professor Jacob in 1995. They have seen they put this thermocouple just above the 2 centimeter of this net, okay, and one thermocouple inside, and they see the 24 hours graph, how it goes. So inside, you can see they maintaining the 28 degrees centigrade, and outside we have the temperature variation is there, okay. So just like thermoelectric generator, okay, what you are talking about, and so this is working as a thermoelectric this one this generator. When the temperature difference is there, the voltage will be generated. So now we start from the late Jacob Ashley professor who have given this one. What he was thinking, we have the two protein there. One is the fibrin, one is the seracin. So he thinking this protein working as a PNN, okay, semiconductor, and this elements is the dopant are there. So he's saying that these are maybe semiconductor. We have this PN junction. Okay, dopants are there. So the current will be generating. Okay, this is he have given in his paper. But this is our silk cocoon membrane is the generate electricity. If yes, we can harm the electricity from the useful node. So this way we was thinking when we start the work, seeing that when the water molecule trapped in the fabric matrix of the SCM, they interact with the natural occurring the ion forming elements, which already we have seen the EDX, they are available there, and generate the ionic mobile charge carrier. And this charge carrier can flow the electricity in the silk cocoon, okay. And this will be with the temperature, that charge will be increased. So this way, okay, then we make the small device of that. We will use the two electrodes, okay, put this membranes between the two electrodes and give the different conditions. If we can able to see any current there, when this is the dry conditions, the current is very less. When we increase the moistures and NaCls, we have given the different atmosphere, the current will be increased. Okay, so then we can see the electricity from, then we see what happened with the current and voltage with the temperature. So we see the temperature and voltage will be increased at 60 degrees centigrade. So then we did the various experiments to understand that one. We see the sharp increase the current around the 60 degree. With thermal event also we observe the heat flow, how the heat is flowing in this one. We see also the NMR study of the carbon, hydrogen and nitrogen, Na. We did the NMR. We see also the sodium ion mobility in this one when we are in the NMR studies. We also see the increase the charge mobility around 60 degree when we have this heat flows and this thing. So we did the various experiment to understand what is going on, and this we are thinking the current flow in we expose the temperature with the humidity and water molecule with the temperature and humidity. When we move this, so the water will be trapped there and they interact with the protein and the ion forming this one. Here actually interaction between the protein with the water is also there, and the Tg, if you see the temperature of the Tg, this is around 120 degrees centigrade, but with the water the Tg will be decreased, and around this reach around 60 degrees centigrade. This way we are seeing this enhancement of the temperature in that temperature. So then we say, okay, we simply what we did, we take the cocoon, we put the two electrodes, and we put the moisture atmosphere, and we put the LED. Okay, and the LED will be continuously, just like a small experiment, we did that one. So we are saying where we have the waste and waste basically in the nuclear plant, thermal energy, steels, where we have the waste, heat and humidity is available. There we can put this the device and continually generate the electricity using that one. And it's, recently actually we see this one recently you can see this temperature different inside than outside. Also when we have the temperature different means humidity is changing dry and wet. You can make the just like a device, an energy storage device using that one. They're working as a cycling. We did the cycling. We make the small device of that one in the series. We put in this device in the series and we did the cycling of the dry and wet. When we do the dry and wet, we can store the energy. So that is also recently we did some experiment there, and this we observed that one when we put this one. And another important this one, because this making the home himself, how this is important, that one we simply do the experiment. We use the silk cocoon, we pyrolysis at the 400 degrees centigrade in nitrogen atmosphere. We have the raw carbon. We purify this one and we get the this graphene oxide. So through this one we can fabricate the graphene oxide. Okay, and we did closely we look how the graphene sheets are looking. We did the Raman spectra, see how that works. We see the magnetic properties also we are observing in these graphene oxides. And so this way we try to make the supercapacitors using this one, using the highly nitrogen doped supercapacitors. So in this case we use the argon atmosphere. Okay, carbonizing the argon atmosphere 400 degrees centigrade. We have the nitrogen dope there. We check the supercapacity in these properties and this one. So why supercapacitor is important? Okay, then nitrogen doping. Okay, we can increase the conductivity. We have the supercapacity property can be enhanced. The stacking will be separated. Okay, then we have the one functional materials. Functions bonds are there where we can make the biosensors. Okay, so we are getting. So in our work, actually, this is a worldwide people are trying to dope the nitrogen in the graphene. Okay, and they are using the thermal treatment for this purpose. Okay, they also do the hydrothermal. The nitrogen percentage you can see they can vary only up to 10% in the case when we go the temperature 300 to 800. In this case, when you're using the silk, we have the temperature 400 to 600 and highest nitrogen doped materials we are reported naturally. This is nature is given to us. Okay, so now we see how the temperature will be playing the role. We go in the different temperature, this one, and we see the specific capacitance, charge transfer, equivalent series resistance will be modifying, changing with the nitrogen composition or temperature. So we can say these are nitrogen doped graphene supercapacitors. When we have the current collector, we use the graphite sheets. We have the nitrogen doped graphene, and we have the electrolytes. We can use PAV or this thing, and we can develop the supercapacitors using this one. So, okay, now this is actually these are our interest to see what is going on. Okay, and we know the bed and give the echolocation to the navigate the dogs. Okay, he can find out when you send the waves, ultrasounding waves come back, and he know the direction where so why our interest is developed here. This bat like the silk moth. He generally in the night, he tried to eat the bat. So our thinking was, nature never did the injustice with any person. Okay, only we are maybe we unknowingly doing this job, but not the nature. So if he have this capability to find his food, so definitely our silk moth also have something. He can know the bat is want to eat me. Okay, so this way what we did, we just take the various maybe the fur and also antenna wings. So we take the antenna wings of this silk moth, okay, and we'll see the what with the index what percentage what we are having in this one, and we can the weight percentage. Okay, iron, cobalt, nickel, manganese. We can see the what is there inside there, and we also see the shape. All the shapes are looking there, and we describe the cubical shape. We can observe the calcium oxalate crystal also there in case of when we have the antenna, but in the wings case is we have the different with the calcium, cobalt, and oxygen. So try to understand that when the basically carbon is there. Okay, inside this wings we have these calciums are there, and when we did the ESR spectra. of the antria and this wings, we find the presence of the carbon-centering radicals are there. Free carbon particles we can observe in this one, and in case of the both the cases, we see the magnetic of this one properties for this observe that one, and we know the navigation, the animal do the navigation when we can detect the magnetic field of the earth. They will navigate and they will find their way to fly. They will find their way to go there. Okay, they have that capabilities there. So okay, so here the presence of the stable carbon-centric free radicals in the antenna and wing can be used for that one. So we propose here. So okay, when we back to give the sound waves, the ferroelectricity materials we are already observed the iron, cobalt, nickel there. The spin current is generated in the ferroelectric layers. Then we have the paramagnetic layers, the carbon-free radicals, and paramagnetic layers sends the spin current, and okay, and then this position of this bag is coming to eat him. So this is our we propose this one. If we grow structure like this, okay, so maybe so we can maybe able to use the various sound frequencies, various this one, the sound base, all the sensor and device we can fabricate using this type of systems. So now isolation of the fluorophores for the silk cocoon, because we are talking about the sustainability. So we'll see how this is sustainable. Can we are affecting the farmer? If this is a farmer effective technology, then maybe this is not a sustainability. So we see we observe the fluorophore in this one actually. Because fluorophore coming from the leaves. Okay, when it's eating the leaves, the fluorophore is there going in the silk and cocoons, and we observe the image in the fluorescent in the different wavelength. And now we can isolate this one. We have isolated the fluorophore from the silk cocoon, and so this is our method. We adopt this method to get this one, and this is actually for the farmers. Basically, this is the additional product they can achieve because without disturbing this one. So we can have this fibrin there. We have the seracin there, fluorophore there. We can remove the fluorophore. We can purify the fluorophore. Still, we are not going to disturb that one. So they can use the silk for the fabric purpose. So the important comes here, the cost. You can see the various dyes the people are using worldwide. These are synthesis dyes. They're fabricating by the chemicals routes. So we have the PDMPO. The cost is very high. But in the case of the natural dye of this one is very maybe the 100 or 200 rupees. The total cost is coming for the 1 or 2 mg, and you use for the bioimaging. So bioimaging, you can use that dye. So these additional costs will become and for the farmer, and they will be able to survive this one. Now you are also talk about the solar and this thing. So we'll see how the solar part is generating there. So in what we did, we just put the ITO glass. We make this a graphite cathode and anode. Outer, and we think the outer and inner surface is cathode and anode. Okay, and we can put the silk cocoon. We use that one, and we can generate we observe the voltage with the time, and also this is the maybe we have the dye synthesized solar cell of this design, and we use for that one. We are getting the current. Okay, out of this one. So this is we also the same. I'm saying we are isolated the fluorescent from this our method, and we study also that we study the details of this one. I'm not going for the scientific details. So we did this one. Important this one we use this fluorophore also for this dye synthesis solar cell. So we use for the fluorocell coated TiO2. We have the TiO2 anode and cathode. Then UV visible light. When we go there, then electricity we generate the enhanced compared to when we are using the normal silk cocoon. So here we are comparing what happened in the silk cocoon and what is the actual conditions we have that one. So here in the silk cocoon we have the high temperature. Outside we are saying anode. Inside we are saying the inside cover is the cathode. We using the SCM as a semiconductor, and UV centrifuge fluorophore is already there there in the photosensitive dye is there available. And that when we trap the moisture in this one, electrolyte to improve the mobility of the charge moieties. So this is, we are comparing that one. And if we see the actually the various material, what type of membranes we are having. So these are outer and inner, the temperature different are there. Temperature gradient we observe. Also, we observe the gradient for the water. Okay, inner surface is waterproof and outer surface is porous. So porosity is varying. From the gradient, for porosity gradient is there. This is the important part of this one. So porosity gradient is there. Then so we can already observe the porosity outer and inside is there. Then we are having this also we can see the change in the porosity gradient. We can have the fluorophore there. We observe the fluorophore. We are having the calcium oxalate also arranging in the gradient way. The outside is more and inner is outside. So we can observe that one. Then we have this grating oxygen. The oxygen flow will be varying in this one. So if we see the similarity in the both one, okay, we have the water molecule in gradient, porous size in distribution, embedded fluorophores are there, distribution of the calcium oxalate and carbon dioxide. So this asymmetric behavior is very important for the electrolyte. So this asymmetric behavior have create the thermal water, salt and gas gradient in this membrane, okay, and in the outer inner surface, and this is the responsibility for the charge flow. So now we can imagine the electrical circuit also is through this one. We see the electric circuit, the light to electricity converter we can see. We can see the variable resistance in the SCM. We can have the thermoelectric setback generators are there. We have the capacitors are there. So as a electric person, we see the voltage, current, resistance across this one. So this is the fashionable change. When the weather will be changed, accordingly he will modify that one, and sustainability will change these conditions. So now how the brain cell dominate during this our dormant phase. The cell cocoon membrane, they have the inbuilt light, humidity, temperature sensors. They convey this signal to the dormant pupas. Also there the pupa has a light, moisture and temperature sensitivity cell remain active during the dormant phase. So these are basically the electrical circuit total is grown by the nature. We can understand that one they are having. So they have a lot of the applications are there. Okay. So we have the temperature regulators, electricity, and this one, and the lot of the future scopes are there. You can use this material for the various applications. Already some work is going on where they can use for the chargeable batteries. With you, Bangalore, we have discussed I'm just giving the talk, they want to do this one. So they have developed the small gadgets using this cell cocoon, and see they are working. And my dream is this one, self-sustainable zero emission house we can make using this technology. So everything is there. The store is there. We can make this type of house where we are self-dependent. We are not dependent on anyone. So this is the steady nature, love nature, stay close to nature, I will never fail you. This quotes I will feel that you fit for this one.
Thank you, sir, for the fascinating presentation. I request Vice Chairman, sir, to please present a token of appreciation to Singh, sir.
Neil.
Thank you, sir. Our our next speaker would be joining us online. Students, please be seated. We have one more international speaker who would be joining us online. And thereafter, you're free. Thereafter, you'd be free. But please wait for one more session. We have an international speaker, Professor Brian Norton. We are connecting with him. Students, please cooperate. You've been very cooperative. You've been a very good audience for all day long. Please, we're requesting you for another 45 minutes. That's it. You've cooperated really well with us. You're all adults. Please, we request you humbly to please wait. And please settle down. Good morning, sir. Am I audible?
Good morning. Good morning.
So we are excited to hear from our second keynote speaker, Professor Brian Norton from the Technological University, who is joining us online today. Professor Norton's research, particularly in integrating solar energy within building systems, has led to advancement in photovoltaics, glazing, daylighting devices, and solar heating. He is specially noted for his work on phase change materials to cool photovoltaics. He has supervised over 60 doctoral students, and his research with over 16,000 citations and has an Edge Index of 65 has significantly impacted the field of sustainable energy. Today, he will be sharing his expertise in a talk titled Energy Materials. Although Professor Norton couldn't be here with us in person, we are very grateful for his virtual presence. Please join me in welcoming Professor Norton online. Over to you, sir.
Good morning. First, can you hear me okay? Yeah, okay.
Yes, sir.
Let me see if I can share my presentation here. Can you see my presentation?
Yes, sir.
It doesn't seem to be moving forward. Let me just stop sharing and just go back to that. Hold on just a second. While we get the technology sorted out. Otherwise, I'll just present without the slides. We'll see how we go here. All right, let's just see if we can do this. Okay, so if we go to there and share. Okay, now this doesn't seem to be moving. Does anyone know how I get it to move forward?
So you can use your arrow keys on the keyboard?
Yeah, okay, let's see if that works. No, it doesn't work. That doesn't work. Hold on, let me just...
The
No,
down?
that's not working. For some reason, my slides won't work.
So you can either share the entire screen, or you can share through the special window. So you can choose either of the two options. But if you choose the entire screen option, then in that case, you'll not be able to see the audience. You'll only be able to be in the presentation mode.
Let's see what happens if we do that. The entire screen and share, that might work. Let's have a look. No, that doesn't work either.
You can just switch on to the presentation. So that way you'll have to go to the presentation mode.
Okay, bear with me, everybody. My apologies for this. Okay, if I go to the window, all right, and I pick the display, okay, and share, right, share.
So the left, right arrows or the up and down arrows should be able to help you maneuver.
Yeah, it doesn't seem to want to play. Okay, let's not, what does that one do?
Ask him to turn on slideshow. Sir, please turn on the slideshow option. Please, at the top there is this slideshow bar. Please navigate there, and there would be an option.
Okay. Let me maybe do it a different way. Let me just perhaps, yeah. What I will do is maybe talk without the slides, because I think we'll spend so much time trying to organize the slides, that'll take up all the time, okay? And maybe talk about new energy materials in a general sense without using the slides. So first of all, it's
sorry for interrupting you, sir. If you want, you can share the slides with us. We will navigate the slides for you, and you can keep on presenting.
No, don't worry about it. I can talk. As long as you can hear me.
Yes,
I can talk without the slides. That's not a problem.
Sure, sir.
It might even be better. It might even be better. You never know. Okay, let's see.
Sure,
Okay,
sir, sure.
so we're talking about new energy materials. First of all, what is energy material? An energy material is something that can give you advantages in terms of efficiency, lower cost, lower weight, less toxic materials, more sustainable materials, etc. So it's a huge gamut of different things. And fundamentally what an energy material is something that aids the conversion of one form of energy into another, or aids the transmission of energy from one place to another, or enables you to store energy. And indeed, fundamentally what it's about is, if you look at renewables, for example, which are highly distributed, you've really two choices in getting what are called high capacity factors, high matching of the supply to the demand. You can either move the energy in space, in other words, transmission. So, for example, the sun is always shining somewhere. So theoretically, you could move the energy from where it's produced to where it can be consumed. Or you can move it in time by storage. So effectively, you're storing the energy from when it's produced to when it's used. And technologies for transmission and materials for transmission, so thinking about direct voltage transmission, superconductors, etc., essentially compete with new technologies for energy storage in terms of those two aspects of trying to get a high capacity factor, a high amount of matching of renewable energy supply to a load. So there's a whole gamut of possible technologies that can exist in that area. New technologies are also a complex set of things in that the attributes that you might have which might be desirable in one respect are contradictory to the attributes you might have in another. So you might, for example, want a material that has higher energy storage density, is more efficient in both charging and discharging, for example, in a storage application, but it's more difficult to obtain, has geopolitical implications in terms of where it's sourced from, may be toxic. And so often with new materials, there's a trade-off between the attributes you want to achieve from a technical perspective and the wider environmental and economic factors that come into play, health factors as well, for example. So in choosing energy materials, there's a huge variety of different factors that come into play. Also, those factors change with time. So if I give you one concrete example of that, over many years there were new materials being developed for concentrating solar energy onto photovoltaics. And the reason for that is that photovoltaics were expensive and concentrators were very cheap. And you get very cheap concentrated materials made out of polycarbonates, polyacrylics, etc., as well as glasses, etc. What has happened, as we all know, is that the cost of photovoltaics has gone down very, very rapidly. And that means that actually photovoltaics are now cheaper than concentrators. So developing new materials for concentrators, except in very particular applications where the particular type of photovoltaic works better under a more concentrated flux, is no longer a good idea. So the changing cost of different materials has changed what opportunities there are for materials in those applications. And you can see similar things in many, many other systems. But I can give you some examples of where materials are continuing to develop. One of the key challenges in photovoltaics is their thermal behavior. And as most people in this room will know, that the efficiency will be going down for typical solar photovoltaics by about 0.5% for every degree Celsius temperature rise. Now that is inherent to photovoltaics because there is, for a single junction, for a single exoterminator junction, you're going to have what's called a Schottky-Kiesel limit, ultimately a limit of around about 32%, and the rest of the energy is going to produce heat. That's just a thermodynamic reality. So a lot of the issues to do with photovoltaics are to do with their thermal management. And so you see a lot of new materials being developed to do the thermal management of photovoltaics, and indeed a lot of new applications. So for example, if you look at new applications, for example, agri-photovoltaics, where photovoltaics are matched to agricultural production, or photovoltaics, the advantage of those, as well as making better use of land or water, is that in both cases, transpiration, when you've got agricultural photovoltaics, or evaporation from the water beneath in floating photovoltaics, are cooling the photovoltaics. So you can do system perspectives of how to cool them. But there's also a lot of technological interventions, one of which I was responsible for originally conceiving and developing, was the use of phase change materials to cool photovoltaics. And essentially what happens there is that you have phase change materials which change from solid to liquid at a melting temperature and absorb a large amount of latent heat at that temperature. They radiate through the photovoltaics to the night sky, are solid at the beginning of the day, and then provide a heat sink for the photovoltaics over the course of the day. And that sounds very simple to do, and indeed, in essence, it is. But the realities are much more complicated. One has to make very careful choice of the phase change temperature, such that you're not absorbing heat from ambient, you're absorbing it from the PV. And you've also got to get very effective heat transfer into the phase change material. That's more complicated because as the phase change material melts, the melted material floats and convects within other material in the phase change material, and the phase change material effectively acts as an insulant. So a lot of activity around new materials in that application is around enhancing heat transfer, which you could do with various augmented heat transfer services, like fins, for example, but also introducing things like nanoparticles, larger conducting elements, etc. Or indeed looking at multiple phase change materials, encapsulated phase change materials, etc. Also, these systems are going to go through lots of cycles. Every day they're going to be melting, and then at night reconstituting with radiation of the night sky, the next day melting, etc. So one of the big challenges with these kind of materials is that they don't supercool. In other words, they actually do re-solidify, that they could maintain both the heat transfer characteristics and their latent heat characteristics over multiple cycles. So lots of activities around those kind of materials. Now, one very, very strong example of an application of new materials that is critical to the long-term performance of photovoltaics, but ironically is not a photovoltaic material. Similarly, batteries also have thermal management issues, and similar kinds of systems can be introduced there. The key challenge there, unlike the challenge in photovoltaics, is that many battery systems are to do with mobility systems. They're to do with electric vehicles and such like. And so weight becomes an issue. So in addition to the factors of getting good heat transfer, good latent heat to remove heat, etc., one's also looking to get a very, very low weight of the system. Now, that also can be accomplished by having a very high latent heat because your storage volume reduces. That then presents an issue because the highest latent heats are at the elevated melting temperatures, and most of the phase change temperatures that you need in most applications are not at high temperatures. So again, gives you some illustration of some of the complexities that emerge. Another particular opportunity around new energy materials is nanomaterials, quantum devices. There's a huge number of reasons for this. Quantum phenomena themselves can present certain opportunities for absorbing radiation at one wavelength, re-emitting it at another wavelength, which gives you new opportunities in terms of photovoltaics, in terms of collection systems, in terms of being able to manage rate of heat transfer. Also, you've got in certain nanosystems very large available surface areas at the nanoscale, which gives you opportunities for supercapacitors, for electrical energy storage, and indeed for holding certain molecules in place and releasing them with certain stimulus in the system. So quantum effects, nanoscale effects are introducing a whole range of new materials, both in energy storage and particularly in photovoltaic energy collection, and indeed in devices for light management for photovoltaic. So a lot of things emerging in there. If I can give you one example, you're now seeing what are called luminescent solar concentrators, where you have a material, a dye or a quantum dot. Quantum dots will be preferable to dyes because dyes can degrade in ultraviolet light. What a quantum dot is a small molecule. You can vary its size, you can engineer its size, so that it absorbs and re-emits at particular wavelengths. And any particular solar cell, for example, has a very particular response to the spectrum. Up to the band gap, it will absorb very efficiently, and that absorption will decline away from the band gap. With a luminescent device, one can absorb radiation at a variety of wavelengths, and with the quantum dot, for example, by engineering the size of the dot, re-emit at wavelengths that the solar cell can accept. So the parts of the spectrum that are normally not absorbed by the cell become absorbed by the cell. And actually, interestingly enough, for solar cells, for example, organic solar cells which degrade in UV light, you use the same phenomena to move the UV light to be in part of the spectrum where the cell can use it rather than be degraded by it. Now, one interesting thing about these kind of systems is that you can engineer them such that if you had a window, for example, in a building, you could let the visible light through, the light that sits in the visible spectrum. The rest of the light can be re-emitted by luminescent material on the window outside the visual range, so you don't see anything happening. But that light is going to the edges of the window, and solar cells can be placed in the edges of the window, in the surround, in the frame, okay? And effectively, you've then got a transparent window in the visual range, and indeed you can control that transparency such that it just lets in the light and doesn't let in the heat, okay? Or the rest of the instant radiation is transmitted transversely through the glazing, through re-emission from quantum dots, and is collected at the edge, okay? Now, this in itself then presents an opportunity in that you've now got a window that is both letting light through and collecting solar energy, a transparent window and it's collecting solar energy. And one particular application of that is then actually having a switcher material. And there are a variety of switcher materials, from suspended particle devices where particles are reoriented in a magnetic field, so that one orientation they let light through, and another orientation the window is darker. It's not entirely dark, but it has a level of opacity, and you can control the solar gain. Now that requires electrical power, and if you have a transparent window which can generate its own electrical power, it can produce the power to control its own transparency. So you're seeing here a occurrence of new materials that are both allowing you to redirect light to solar cells, alter the spectrum, and cells acting more efficiently, and the electricity of those cells to then power a switcher material which then can alter the transparency of the glazing to avoid overheating, to avoid glare, or to provide privacy. Okay, so a whole range of new materials, and you're beginning to see products in glazing systems for energy efficient buildings, in the climate I'm in, to let in solar gain and allow heating, in other climates, for example, to just let in light, reject heat, and indeed reject heat to the night sky at night and produce cooling sinks for the next day, etc. A whole range of possible applications there. And that idea of also rejecting heat during the day is also gaining a lot of traction, with a whole range of new materials seeking to exploit the long-range window to the sky that always exists. There's always about 40 watts meter squared coming from a surface, even on a sunny day, to the sky. There's always a radiant heat transfer there. But normally during the day, it's overwhelmed by the solar gain in the rest of the spectrum. But if one device spectrally selective devices, one can get systems, even in sunny conditions, are cooling to the sky. Now, that's common at night. As many of you know, a clear sky at night will produce rates of cooling which will produce ice on the ground the following morning, even though the air temperature is much higher. This is doing that during the day, okay? And again, new materials of that kind of application. So there's a whole range of new coatings using quantum effects that are seeking to manipulate the spectrum in photovoltaic applications, in switchable applications around glazing, and in applications to seek to have radiant heat transfer to the sky for cooling during the day. So a lot of factors in those. Now, if I just step back from those examples and look more generally what the challenges are. As I said earlier on, a lot of the challenges with new materials is not simply their technical characteristics, and there tends to be a lot of research on their technical characteristics. So, are they more efficient in doing what they do? Are they reliable in doing what they do, etc.? Those kind of things are very heavily researched. What is less researched, but is equally important, is the kind of trade-offs. If you look at things that are going to be put into buildings, for example, and indeed in many applications, the flammability and the toxicity of materials becomes very, very important. And many of the materials that are developed do not have those characteristics. So they might be very interesting in the laboratory setting, but are not going to go to the commercial setting because the toxicity and flammability issues mean they're not safe to apply. So that's one dimension. But the other dimension is the dimension of the design and packaging of systems to use those materials. And this is an area which needs a lot more research because there are ways of using materials that minimize the amount of material you use, and there are equally ways of using materials which do not do that. And if I can use an analogy, one can have structural systems that are composed of solid steel elements, okay? But you can get equally strong structural systems that use tubular steel elements. In a tubular steel element, there's a lot less metal, okay? Well, the same applies when you're looking at applied materials in energy collection applications, energy storage applications. How you deploy the materials, how you design the system, where you create the services, their adjacency and connection with other parts of the system becomes a very, very important factor. And that aspect of design, that aspect of what's called in the electronics industry packaging, is a much less researched area, but is actually critical to the success of many materials because you want to use the minimum amount of material to maximum effect. So for example, there are devices which absorb one wavelength and re-emit I don't know wavelengths, that is luminescent concentrators, and they are employed in photovoltaic applications and needed applications to get daylight into buildings and things like that. You can have those materials put within a monolithic material, so within an acrylic substrate, so you've got quantum dots in acrylic substrate, and that works effectively, okay? But the acrylic substrate itself has an extinction coefficient. Light gets reduced as it passes through it, okay? Another system is to actually have those quantum dots not in a matrix, not dispersed in a matrix of material, but placed on the walls of a light guide. And so that they absorb, they re-emit, but their transmission is then through air. And obviously the optical losses are zero because you're now transmitting through air rather than through a solid material. Now, because you've got the emitting materials at the walls of the system rather than within the system, the amount of material you can get is less. So you've got less conversion taking place, but you've also got far less losses. And there's a trade-off within that system. And that's just one example where how you choose to deploy new technology, whether you choose to deploy it within a medium that has other properties or in mediums that have very desirable properties, but the particular attribute of the technology is reduced because the amount you can put in the system, become very, very particular trade-offs. And that kind of work in both in thermal energy storage, in a lot of quantum devices for spectral modification, in a whole range of applications around using near field effects to inhibit radiant heat transfer between systems, is an area which needs a lot more work and a lot more optimization. The opportunities for new materials are considerable, and they are, as I say, driven by aspects of trying to get better efficiency, lower weight, better storage capacity, lots and lots of factors. One key factor, however, that's coming through is less embodied energy. And this is important because in making things, there is energy from fossil fuels, etc., embodied in those materials, particularly if you look at things like cement, ceramics, glass, steel. A huge amount of energy goes into those materials, okay? And in certain contexts, the embodied energy is similar to the energy that the device uses operationally. So seeking to reduce the embodied energy is critically important. Now, we can do that at the process level, obviously alterations to the manufacturing process, or indeed electrify the process and supplying the electricity to the steel, cement, glass production from renewables. You do it at that end, okay? Nevertheless, at this point in time, there's still a lot of fossil energy embodied in current materials. And in the future, let's suppose that those manufacturing processes do electrify, there will be a lot of renewable energy consumed, indeed the majority of the renewable energy, consumed by those production processes. So seeking to reduce the use of those materials is going to reduce the amount of fossil fuels embodied, and in the future, reduce the need for excess renewable energy capacity that is not needed. So a lot of work is going on in seeking to have materials that are more bio-based, so cellulose, polysaccharides, those kind of materials, which are far more sustainable, are effectively carbon sinks if done correctly. And you're seeing that in certain energy storage systems like batteries, for example. You're seeing it in insulation systems, and you're even seeing it in some aspects of the substrates for photovoltaics. So a major strand is that aspect of looking at the overall environmental sustainability of materials. That also brings you to a whole lot of dimensions of how you track materials from their source, where they're extracted, where they're mined, where they're grown, all the way to their point of energy use. And so that you're including both the energy use of their extraction, their processing, and their transport. And that is a whole well-developing area. In a number of jurisdictions, I work in Ireland, which is in the European Union. The new regulations on building products, for example, the Energy Building Products Directive, requires European member states to introduce laws that will regulate the embodied energy in building materials. So these trends are happening, and they're affect both in those countries, and indeed people who export materials to those countries in the future. So many diverse aspects of energy materials. What I want to draw as a conclusion is that materials science is one thing. I think material science always needs to be developed in the context of application, economics, and the wider environmental issues in terms of environmental safety, fire safety, toxicology, etc. And that needs to inform direction quite early on, okay? And there needs to be as much research in those areas as there needs to be in the fundamentals. And also, we need, from an educational perspective, to produce graduates who can have the design expertise to apply new materials in a way that minimizes the use of those materials and maximizes their effectiveness in end applications. Some of the insights I provided today have come out of a whole range of projects, and for those of you who can do these things, if you look up my papers, you'll see the kind of publications and things that we do. We are supported by a whole range of organizations who I'd like to express my gratitude to. And I hope not having the slides has not been too bad. And I'm happy to answer any questions. Thank you very much indeed. Thank you.
Thank you so much, Professor Norton, for your insightful and inspiring talk. Are there any questions from the audience? Oh.
Thank you, sir. I just want to know, because India is a 1.4 billion country, so we have large human resource development activities here. So do you encourage joint projects with Indian researchers? And if, what is the modalities? And Indian government is also funding joint projects with different countries. We have MOUs with about 40 plus countries, maybe including Ireland also. So what about internship from Indian students at your place? Thank you, sir.
Could someone repeat the question, because there's a lot of echo in the room?
Yes.
Is it possible to repeat the question? Could maybe the...
Sir, we have large number of students studying in different courses in the country, and this area of energy material is a hot topic. So we would like to have a collaboration of Indian researchers with your team. This is one question. Second is whether you also encourage Indian students to be part of your organization as a training or as a project.
I still can't hear. The sort of the microphone at the we did the introduction. Her microphone works better. Maybe you just repeat the question from there, because there's just a big echo in the room. My apologies.
Yes. So is this audible? Hello?
Hello. Yep.
Yes, sir.
Sir, we have a large number of students studying in different courses in the country and across different universities and institutions. And this energy materials is a hot area of research. So I just want to know whether there is a possibility of joint research activities between Indian researchers and researchers at your university. Number two, whether there are some opportunities available for Indian students to have some sort of internship or training, to have a collaboration or human resource development activity at least.
Okay, yeah, I understood. Apologies for getting you up on the stage. That's much clearer. Yes, I mean, generally, we work with PhD students and postdocs in my context, and we will have had students all over the world work with us as doing PhDs and doing postdoc positions. So that would be there. Having students as for shorter term visits is more difficult because we've got to slot them into existing projects. That can be a more challenging. But I'm always open to discussion and see what opportunities for collaboration there are. But certainly if there are students who would want to do PhDs, there are various funding schemes that support that. The challenge with shorter term visits and faculty exchanges, etc., is funding, okay? But certainly happy to discuss collaboration. And indeed, I collaborated with many colleagues in India over the years, been to India many times, and we've done research in India, particularly, for example, on PV cooling, on aspects of solar concentration, and some work on solar cooking, for example. So there's a lot of opportunity for collaboration. So if anyone's interested in collaboration, just write to me and we can discuss it. The main challenge is, because it does take time, the main challenge is developing new things that are going to get funded. Because the cost of it is the main issue. And certainly where I am, Ireland is a very expensive place to be, and it's important people are properly funded here so they can live properly. So that is the issue. But yeah, collaboration is something we do a lot of, and I would be keen to do more of. So happy to discuss. Easier at the PhD and postdoc level is my summary.
Thank you, sir. We also have a request, if possible, please share your presentations or a video of your presentations with us so that we have a better understanding of the topic.
Yeah, happy to do so. Happy to send the presentation. No problem.
Thank you, sir. Thank you so much for joining us today, and thank you for sharing your thoughts.
Thank you.
We'll now take a short break for lunch. I kindly request everyone to return in time for the technical sessions scheduled to begin at 3:15 in their respective rooms in keeping with the schedule. Thank you all.